Okay, so we've built models of either hexose monosaccharides or pentose monosaccharides. So you're looking at either a furanose or a pyranose. And then this one is glucose. We're looking at the anomeric position, which is C1. And either the hydroxy group is down or the hydroxy group is up. Okay? So, Megan, you did yours with the hydroxy group up, is that right? Okay? So that's your beta form. And then hydroxy group down is the alpha form. So which form do I have here?
You have an alpha because you're down.
That's right. I have the alpha form because it's down. So here, there's the OH, right? And you go to the anomeric carbon, and this one is down. Good, good. So that's in the chair form. You can see everything is either axial or equatorial. Axial is straight up and down. Equatorial is what's around the equator, and they are either slightly up or slightly down at an angle. Okay? What about the different form for this one? What would it be?
Talking about the boat.
Oh, yeah, boat. What was the one that we were looking at in the case study? It wasn't a boat or a chair, it was a half chair, so let's look at that. So you just barely move it, and there it is in the half chair, where this side of the ring is planar, see it? And this side of the ring is cockeyed. And then if you move it into the full boat, then there it is, and you can see the less favorable interactions between these two areas, okay? Yeah, so that's the more strained regions, and the more strained conformation, the less stable of the two, and then that is the chair. Can you walk it? Can it go into the opposite chair? Can it go into the opposite chair?
It's not as stable.
Okay. It may not be as stable based upon, see, the interactions between the substituents, right? So you may have steric interactions between those. That looks happier because now those are in the equatorial position. You see how that happened? So flip it back the other way. That's a 1,3 diaxial interaction. Those aren't very good. And so we flip it back, and those are now equatorial. There's still some diaxial interactions, but they're hydrogen diaxial interactions, which is not as bad. Okay. Did you all compare to anyone else? Anyone else? Did you look and see if did you make the alpha? Did you make the beta? So take a look at that with your neighbor.
You made beta. You made beta, right? And I don't remember what I made.
You made alpha. You got your alpha.
So is it always where you have to have the oxygen? Like at the top of the ring, so to speak, from your perspective, that's how you orient it? Like you couldn't do this, cause then, or like you couldn't do that. It has to be the,
And then this one should be.
cause like, you see what I'm saying?
Yeah. It's a matter of perspective.
Yeah.
Oh, wait, hang on. This one's.
So
All right.
each of them-
So now, how would you make the L form of this? How would you make the L form of this?
Is that whenever it's, not close?
No? How would you make the L form of this? D and L would be enantiomers of one another, so how would you make the L form?
Flip all the chiral centers.
Flip all the chiral centers or make the mirror image. Yep. Flip all the chiral centers or make the mirror image. Good.
All chiral centers. But
So-
all the carbons, I mean, except for the carbon that's.
Except for
associated.
carbon number 5,
Okay.
right? Yep. Okay, so now coming back, how do you form the alpha and the beta? How does that actually happen? Okay, I'm not gonna give it away right now. If you go back to the previous slide and you look at the hemiacetal formations, okay, and you pay close attention to this, there's something about this leading to chirality that will actually give you insight into how this process happens. This slide is horrible, and I already told you that, because first of all, by organic chemistry rules, that's a carbon and that's a carbon with 2 hydrogens, and that's not true, okay? Why didn't they just make a circle or a semicircle, right, to connect them? Because they're biologists, that's right. Okay,
That's true.
so you will, again, like I said, not see that version, but instead you'll see the Hayworth projection and the Hayworth version. So talk it out with your neighbor and take a look at the acyclic form of the D-ribose in the middle and talk about how you might get the alpha or the beta forms. Go. You might even take your model kit apart at that position and think about it from the perspective of your model kit.
I can tell whenever they line together.
This comes apart. Yeah, and then this carbon will have double bond and double H. Oh, yeah, it would be double bond. So that was the anomeric interchange. Would it not just be this pops off? And then.
The question is mechanistically, how does the alpha and beta forms actually form?
Isn't, that would be, ST2.
Would it just come down to,
Because it would be the alpha trim.
would it maybe come down to, it's like the environment is in whenever it's made, because
The only real difference is the orientation of the hydroxy groups. No, I'm thinking the NL configuration.
The other thing that you can do is you can also take your hexose, if you made a hexose, you can take it apart and make a pentose. And then vice versa, if you made a pentose, you can take it apart, just like it shows, and reform it to make a hexose. You might have to put one on it, Caitlin. So like here.
Yeah. this
I think
the-
thought was the-
See, like here, if you don't,
You have two.
No, I think it double bonds with the,
Well,
that
that's the
hydroxy
most-
group, the alpha
I'm
beta
trying to
hydroxy
get
group.
through this here. This is just there.
Right.
I'll leave you to it.
Oh,
And
sorry.
then on this carbon, we'll do RH, I think. Well, wait, can I just?
So
no,
this is,
sorry, beta's up.
this is the D
Alpha's sorry.
configuration.
You can cut up just a little. Beta is different from all the other ones. I don't know where it came from. How that was.
So that's how you get the OH on the
Oh,
first
okay,
one.
the O.
Or you can double bond down.
So this kind of.
Because D-ribose, right, initially D-ribose is like a chain like this, right? So we got so many OHs and O's, those D-ribose, so
This one here,
hydration, take out the water
to form
and
the,
hook by
beta,
I think that's when it's.
and this one
Yeah, so I think what we could do, maybe like have this oxygen, snap off this bond here, get close up to all these OHs, best way to do
Nope,
this is
sure didn't.
by just
That's not the
removing
worst thing.
OH and.
That's definitely not the worst thing I've
No,
seen.
you're
We've snapped that a lot.
losing the hydrogen on the oxygen.
Haven't met Megan.
Yeah, and you're losing the double bond.
Oh, I bet I've
So
seen.
maybe the ketone.
Do what?
Grabs a hydrogen off.
Wait, and how many people are in on this now? Everybody. Well, now I don't know what someone's happening.
So maybe that.
I don't
the
need to know
oxygen
either.
is gonna go get oxygen. The double bond is gonna go over there and give that oxygen.
I feel like I'm gonna go home this weekend and snap, and my
Then
family's just
that
gonna be like,
OH
I taught my
is
dad
the last
snap
hydrogen,
us.
and that oxygen is gonna go. Okay, that's awesome.
I think I accidentally made a
So
motion.
yeah, any hydrogen.
This whole thing started with Kate and Helen. Yes. Technically, yeah, but like technically.
Technically, I started here.
Look, yeah. The wormholes, is over here.
I want to know.
I can stay. I got up to a cleaner to show.
I'm still trying to build right behind them.
Might take another 10 minutes. Okay, look, you know how to do this? It was like this.
For those of you in organic, what happens when you attack the carbonyl? We just reviewed it today.
You
Potential
create a new,
control.
stereo center, don't you? And so
You
get-
create a new stereo
and you
center.
get a,
What is the process of that called, actually?
Of attacking?
No, the inherent properties of the aldehyde or ketone, which then create a new stereo center. You may not even know that. I don't even know.
It's trigonal plane.
I don't even know. Okay,
It's no longer trigonal plane.
that's fine. Okay, you probably see
Got
that
that
I drew
down.
them in the plane up here on the board. Okay, so it's trigonal
I
planar.
forgot what that type.
What, so, when it attacks, what happens to these electrons?
They resonate up.
They resonate up to here, and then in order for that to go to there, what has to happen?
Intermolecular shift.
No?
Proton.
You just gain a proton, right, for a quench. But again, what makes the OH be up versus what making the OH be down? What has to actually happen for that to take place?
Is it good for SN2 reaction?
Okay, prove it.
So if you take a bonds apart, without actually destroying the whole molecule, which would be great, I don't even know where this came from. Hold on, the whole thing just fell apart.
It's okay, it's all right.
Okay. But anyways, you can either have it to where it can be down right here, or it can rotate, then it can be up. That's just kind of how I did it.
Okay. So I'm gonna go ahead and take the glucose apart, and I'm gonna put one of these in. Actually, to make it a little more accurate. Okay. So, there it is. Alright, so there's the oxygen that's doing the attacking, okay? And there's the aldehyde, right there, okay? So, Megan was saying, when it's apart, you have free bond rotation about the aldehyde. See it? Okay? So in order to form the alpha, where does the aldehyde have to be oriented?
Has to be down.
The aldehyde has to be down before what happens?
The attack.
Before the nucleophilic attack happens, okay? This is the concept of prochirality, okay?
Oh, yeah.
So we say that the aldehyde is prochiral, and therefore if it's oriented down, this is actually attacking one of these two faces, okay? This one on the left, this is the C face. So, this one here, this is the ray face. This is not in your book, okay? This is all organic chemistry. So the attack either happens from the ray face or from the C face, and that is what's responsible for the chirality changes or the difference in chirality, okay? So take a look. Aldehyde's down. This thing is coming in and attacking here, okay? Versus aldehyde up. And look, it's the opposite face, right? So this one is the ray face. If you're looking at it from here, that is oxygen to carbon, so that's the ray face. So when you come in and you attack from the ray face, that gives you the beta form. Flip it over, attack from the C face, gives you the alpha form. Good, Megan. Nice work. Okay? So this is all about carbon-carbon bond rotation. Yeah? Do you know which way it's going to form? Okay. Does it have an equal chance of forming in both?
Depending on the conditions.
I would say depending on the conditions. Okay. So maybe enzyme catalyzed process that stabilizes one versus the other. I don't know. Yep. I'm not a biochemist. I couldn't tell you. Okay. But I do know that if it was organic chemistry and you had these in solution, they would have an equal chance of forming either from the C phase or the ray phase to form the alpha or beta form. Now, that being said, that would also probably depend on the position of the other hydroxy groups as well. So maybe there's some sterics involved with that. I would say that that's probably a good chance that that is the case. Okay. Any questions on that? Okay. This was kind of the activity I was going for. I changed that just a little bit. So we already went through and did what I wanted to do for that. The interesting thing about the 5-membered pentoses, or the furanoses, is that they have these weird, wonky, out of plane orientations. How many people still have their pentose put together?
I did, everywhere I did, I noticed that, but yeah, it's like.
You have one? Okay. Go ahead and try and walk it into this is called the 2-endo. This is the 2-endo conformation. So try and make it go into the 2-endo conformation.
Shoot.
So the 2-carbon is the one that is just kind of sticking up out of the plane. Can you get it?
What do you mean by that?
Yeah?
Like, that's one, that's two, so
That?
one's sticking out.
Mm-hmm. That's it, right there. You
Okay.
just did it. Yeah? Devin, did you try that?
Yeah.
Did you have it in that?
Yeah.
Okay. The other one is just the 3-endo. It's just the 3rd carbon, and the 2-carbon goes back into the plane. This is really interesting because in organic chemistry, you don't consider these different conformations. Why do you think they're considered different conformations in biochemistry?
They could do different things.
Possibly.
Or it could have something to do with the enzyme complex.
I think it's actually because they can be held in those conformations. They can be restricted in those conformations. In organic chemistry, these two different conformations are not conformational isomers. They're not considered conformational isomers in organic chemistry. They are literally just considered, what?
Like just free form.
Yeah, basically just different free form movements that could be achieved in solution, right? Not to say that if it wasn't a crystal that you're not going to get, some vibrations, but in solution phase, this is happening all the time, okay? Those types of movements are happening all the time. But in biochemistry, they are two different conformations. So those are called conformational isomers. So we have stereoisomers, which is the D and L, right? But we also have the alpha and beta forms. Those are a special stereoisomer. What are the alpha and beta forms? What are they? There's a special name for them in biochemistry. It's the anomeric position, so they are anomers to one another. You need to know that anomers are diastereomers. Anomers are diastereomers. They only differ in one configuration. Okay? The other one is an epimer. So if it differs on a different carbon, okay, so let's go back. If you look between these two are anomers of one another, right? But let's say you took the 3 and you switched the 3 up. If you took the 3 and you switched the 3 up, first of all, it would be a completely different name. Don't ask me what it would be. But they would be epimers of one another. Epimers are still diastereomers.
So then what's the difference between an anomer and epimer?
An anomer only differs on the anomeric carbon. So alpha or beta are anomers. Epimers are different on one of the other chiral centers. Either way, epimers and anomers are both considered diastereomers. Any questions on that? Okay. That's all I had for you today. So you guys get out early. Go enjoy some sunshine. If you borrowed a model kit, make sure it gets put back, please.